Okay, so this is 31.9. This is RC circuits. So we can now combine our knowledge of capacitors and resistors into the RC circuit. The RC circuit just has a resistor and a capacitor. We can look at two circuits, one where we are charging and one where we are discharging. Okay, so let's look at the charging mode first, if I can get this thing to work. So we will first consider charging the capacitor in an RC circuit. Okay, so I'll draw the circuit first. So we have the battery, and then we're going to put them in parallel. So we're going to set it up so that the capacitor and the resistor are in parallel. Let me set this up here. So there's going to be a switch. This will be for discharge. Let me put it in the middle. So let's say this is the battery. The battery has, we can put EMF in there. This is R and that is C. Actually, let me redraw this. I didn't draw this correctly. Pardon me, let me redraw this. I should put a resistor here. So this is R and that is C. And then we'll put this here like that. Okay. So we'll first charge the capacitor and resistor combination, and then we'll discharge it. So this point here, I'll put this point as A and this point as B. And we'll say that when the switch is at point A, we are charging the RC combination. Okay. And when it's at point B, that means we're going to be discharging. So let's look at charging first. So charging. And so we'll set up the circuit to charge. So we say E minus the current I going through the resistor, which gives us the potential drop IR, minus the potential drop across the capacitor Q, the capacitor C. Since the capacitor, the charge is given Q is equal to C times V, so we'll say that the potential drop V is equal to Q over C. So let's write Q over C and set that equal to 0. Okay. So that is from the loop rule. And then we'll say that since I is equal to dQ, let me see, I can use uppercase Q, dQ, dt. Then we'll replace I by dQ, dt. So we'll say that the circuit, the loop rule just gives I minus R dQ dt minus Q over C equals 0. Okay. So this is going to be our main formula that we shall use for charging the capacitor. Okay. And then we'll say that at an instantaneous point, so when the switch is turned, or when the switch is placed at point A, the instantaneous current I can be found. Okay. And so initially when we place the switch at point A, the charge on the capacitor is 0. So we shall say Q is equal to 0. Okay, so we say that initially at T equals 0, Q on capacitor is 0 because the capacitor is not charged. Therefore, we say E minus I R is equal to 0. Therefore, the current in the circuit is just equal to E over R. Okay, that's the instantaneous current in the circuit. It's just E over R. Okay. And then the same way we can say that when the capacitor is charged to a maximum value, the current stops flowing. So when the capacitor is fully charged, the current goes to 0. So we'll say that since the current is 0, then we'll say E is equal to Q over C. Therefore, the charge Q is equal to EC at full charge. So the capacitor is fully charged. Okay. And then we can find analytic expressions for current and charge. At different times as follows. Okay. So we'll rewrite what we have here. So we'll say that using our formula again, E minus R dq dt. Let me use maximum charge instead of the same Q. What I should do is put Qm for maximum charge here, so that I'll distinguish it from the Q that I'm using in the derivative. Okay, so that's a different Q. So I'll call that Q subscript M for maximum charge. Okay, so E minus R dq dt minus Q over C is equal to 0. So we can write E over R minus the Q dt minus Q over RC equals 0, and then we put those on the other side of the equal sign. So we'll say that minus dq dt should be equal to Q over RC minus E over R. Okay. And if you want, you can take the negative sign to the other side, and that will give us dq dt equals E over R minus Q over RC. So we want to now take the factors involved. So let's multiply E over R by C on top and at the bottom. So we say dQ dt is equal to CE divided by RC minus Q over RC. So this should give us RC at the bottom, and then we shall have CE minus Q equals dQ dt, like that. I can, for convenience, I can put a negative sign here, and then I'll put Q minus CE over RC and dQ dt, and then we can divide both sides by Q over Q minus CE. So divide both sides by Q minus CE. So we shall have dQ divided by Q minus CE equals minus 1 over RC dt. Okay. So now you can integrate both sides from 0 to Q max with dQ over Q minus CE, and that should be equal to the integral minus 1 over RC dt, like that, from 0 to T. Alright. So the result for this, you can find this formula in the back of the book somewhere. There's a formula that you can use to do this. I'll just quote the result for you. So when you do this integral, you should end up with the natural log of Q minus CE divided by minus CE. And that should be equal to minus T over RC. This integral on the right is pretty straightforward. You are just integrating over T, since R and C are not variables, so you can integrate over C. So this is your basic result. And from that, using the natural log, we can now rewrite this. So if we take the exponent of both sides, so we can say that Q of T is equal to CE 1 minus e raised to the power minus T over RC. So this is the final result. Okay. You might want to check that at some point. Go through this calculation yourself so that you know how to do it. There is a little bit of algebra before that, but I've cut that short. So Q of T is equal to QM, because CE is equal to QM. Remember, we found CE here at the point when it's fully charged. QM is equal to EC or CE, okay, at full charge. So I can put that down here, QM, and then we have 1 minus e raised to the power minus T over RC. So this is basically the formula for the charge, the way the charge grows on the capacitor when the capacitor is charged. Okay. So the charge grows exponentially on the capacitor as it charges. And we can calculate current also, of course. So we can find current again is a function of time also. We can find I of t, current I of t, from the charge given. Okay, Okay, so take the derivative of Q of t and tell me what you get for the current. What is the derivative of Q of t? Anyone? Q of t. So we're going to do d dt of Qm minus d dt of e raised to the Qm again, e raised to the power minus t over Rc, like that. So I of t can be written, this part goes away because the Qm is a maximum, so this derivative is 0. And then the negative, and there's a negative, that's a negative again, and then we have Qm over Rc e raised to the power minus t over Rc again. And I believe we have Qm over R somewhere, or Q over C. Qm over C is E, so we shall put that in there. So we have I of t equals Qm over C, which is E divided by R, e raised to the power minus t over Rc, where we replaced Qm over C by E. Okay, and then we note that I max is equal to, or I is the current. Let's see, I is the initial current when the capacitor initially starts charging. So this is, let's see, yeah. So that is our maximum value initially for the capacitor. When the capacitor is fully charged, the current has its maximum value at t equals infinity. So I max is equal to E over R. So we can say that I of t, I max is equal to, or I equals I max E raised to the power minus t over Rc. Okay, so that's your current through the circuit. So we now have charge and current in the circuit. This is for when you are charging the capacitor. Okay. So for the RC circuit, the quantity that you have, the quantity RC in the exponent is called a time constant. And the time constant is tau. This is the Greek letter tau. Okay, so we can say tau is equal to RC. So we will see that when the time constant tau is equal to t, then we have what is called, when the time constant is equal to t, then the current is at 37%. So So when the time constant t is equal to tau, e raised to the power minus 1. What is e raised to the power minus 1? So e raised to the power minus 1, e raised to the power minus 1 is 0.368. Okay. So this tells us that we have 0.632 qm. So when the time constant t is equal to 1, it means the charge is about 63% of its maximum value. Okay, the charge is 63% of its maximum value at one time constant. Okay. And then we can see for the current, when t is equal to tau, then the current I of t is equal to I max e raised to the power minus 1, which means that the current is 63% also of its maximum. The current is 37%, not 63. So current will be 37%. So where is that? Okay. So when the time is one time constant, the current is 37% of its maximum. Okay. Any questions on this? So the time constant of at the time constant of about 5, we will see that the charge is now up to 99, about 99% of its maximum value. Okay, and the current would have decayed to about 1% of its maximum at the time constant of about 5, at t equals 5. You can put that into the formula just to check that for yourself. Okay, we're running out of time, so I want to complete the discharging portion quickly. Okay. So let's look next at discharging a capacitor. Okay, so the discharge occurs when we put the switch at point B. So this is our switch now. This is point B. This is B, and that is A. So when we put the switch at point B, we are assuming that the capacitor is now fully charged, and we are just discharging it through the resistor. Okay. So we say when the capacitor is fully charged, we can put the switch at point B so that it discharges through the resistor. And we can use the same formula we had before. So for charging, we had the following. We had E minus R dq dt minus Q over C equals 0. And for discharging, the difference is that the E is now gone, and so we should have just minus R dq dt minus Q over C equals 0. So that's for discharging. Okay, and then we can just say that dq over dq, so minus dq dt is equal to Q over RC. Put a negative on the other side and bring the Q down, so it's dQ over Q equals minus 1 over RC dt. Okay, and then we're going to integrate this again the same way. So we are integrating dQ over Q from 0 to Qm, and then we're going to go from minus 1 over RC, we're going to go from 0 to T dt. Okay. And then this becomes straightforward. We have the natural log of Qm over Q, and that is equal to minus T over RC, and then take the exponent of both sides. So we're going to have Q of T equals Qm, which is the maximum charge, e raised to the power minus T over RC. Okay. And then we can find current. By taking the derivative of Q of T. So if you take the derivative of Q of T, then we'll have dQ of T dt equals I of T, and this should be equal to Q minus Qm over RC e raised to the power minus T over RC. Okay, and using the same items that we found earlier, or actually we can leave it this way if we want. So I of T is just Qm over RC e raised to the power minus T over RC. Let's leave it that way. So this is a current as a function of time. Okay. So that item Q over RC we can call initial time or initial current if we want. Okay. This is for discharging. So that is once you push the switch to B and you start discharging, that current initially will start decaying. Okay, that's your initial current. No, actually that's the initial current and it starts rising, not decays, it's rising. Okay. So Qm over RC is initial current. I. So yes, it is decay. It starts maximum and decays. My bad, I'm still saying it the wrong way. So it starts maximum and decays. Okay. I believe that is it for us. When we come back next time, I'll give you 1 or 2 examples to do on this item that we've covered today. And then we'll start off on chapter 32, which is magnetism, I believe, or the magnetic field. So let's end here, and then we'll come back and continue next Tuesday. Okay. So I'll save it. Don't forget to go to the Star Party. Shanaz will be happy to see you when you go there.
Whenever it goes to point B,
It starts to discharge.
is it true 0 or no?
Is it what?
Does it go all the way to 0?
The current? Yeah, it will discharge all the way until it goes away. So if we had a light bulb there, it will flash high and then it will start decaying slowly until it goes out.
So it depends if it doesn't hold the charge.
It what?
It depends if it doesn't hold the charge.
No, it's going to discharge through the resistor. It won't hold it. That's the whole point. That when you charge the capacitor, first of all, you are charging the charge on the capacitor grows to a maximum and then stops initially, and the current is going this way when you are charging. Now, when you flip the switch, you've taken the battery out, And so this time the current starts off max and starts decaying. So the capacitor discharges to the resistor. And so if you had a light bulb in there, it will initially flash a high beam, and then it will start slowly dimming out to zero. We probably can do that at some point here when you guys next week, so you can see how that looks. This is basically the concept that is used for flash photography. So if you wanted to take a picture in those old cameras, what you had to do was once you flip the knob to advance your film, you are basically charging your capacitor also. When you push the button, it flashes. It charges the capacitor, so that is the flash that you get. In the case that we have, we can let it slowly decay if we put a capacitor that is big enough. It depends on how they set it up. If you set it up so that it discharges suddenly through the bulb, then you get a flash, then it goes off. If you put a capacitor which decays slowly, then it will flash, high beam, and then go down to zero. Yeah. So that's how that works. Yeah. So these are the basic concepts. And the engineers take it and they build all these little devices, but the basic concept is the same. It's just a RC type circuit. It's probably not this kind of simple circuit. It may have other parts to it, but it is just a basic RC circuit, which is discharging the capacitor through a flash. Yeah. Any other questions or comments on that? Okay, so that is it. I'll close this. I'm going to stop this and